Hello everyone, welcome to this video tutorial. In this video, I am going to try the getting started example of the ANSYS Simplorer software. Yes, the twin builder. So in this series of videos, I am going to do these examples, yes, that we have in this getting started file. So the first case study example is the three-phase rectifier. So here you can see the model of the simulation that we have. A three-phase rectifier, we have three voltage sources here and resistance, inductance, three-phase rectifier, a filter capacitor, and the load resistance and the load inductance. You can see the value of components here. Yes. So I'm going to generate this model in the software, in the ANSYS Simplorer, and generate these graphs and compare with this document. Okay, so here we have the results. First, we should generate a new project and let's add the Simplorer design we have here. So here is the component libraries and we have these tabs here. So we will discuss these options. Anyway, so from the component library, we should pick up and place the components in the design view. Yes. So here, let's check. We have the basic elements, circuit, passive elements. So I need to place this resistor. Let's zoom. We can zoom on elements by the mouse scroll. So scroll up to zoom. Also, when we select a component, we can use the control key. Yes, we can hold the control key and press the R to rotate this selected element. So this is the R1. Double click on it to set the value of resistance. The value of resistance could be constant and could be a nonlinear function, right? You can consider a function I as a function of V. But here in this simple example, the value of resistance is constant and it's equal to 10 milliohm. This is the line resistance. Yes. So 10, and here we can set the unit, that is milliohm, and press OK. So in the ANSYS Simplorer, you can set, for example, the value of this resistance here to manually set it equal to 10, or you can set it by a pin, right? By a pin here, you can do calculations, get feedbacks from the model, and using this pin, you can set the value of resistance. We will discuss this later, but here simply I write 10 milliohm and set the value of resistance manually. So we can copy and paste, Control V, this resistance here and here to place these three components. And we have these line leakage inductances here, 0.3 millihenry. So we have inductor, again Control R to rotate this inductor, set the value of the inductance that is equal to 0.3 millihenry. Yes. So copy and paste it here and here. Yes. So when I move the mouse on this square, you can see this cross right here. And when you see this cross, you can click to place wires and connect elements to each other. So I have these connections here. And the next element is the voltage source. So where is the voltage source? Here we have sources, the voltage source, controlled voltage source, Fourier source, current source, and so on. In this example, we need to place this voltage source and Control R to rotate. So here you can see this dot that is in the negative side of the voltage source, right? And you can also propose the reference direction of the positive current. Anyway, so let's set the value of voltage. Here, this is a sinusoidal waveform and the phase is 0. Also, we need to know the amplitude of the voltage. So what is the amplitude of the voltage? We should check it from the next slides. Yes. Yes, we have here. This is the amplitude of the voltage, and this is the frequency. Yes. And we have the phase. So when we select the EMF value, the value of voltage is constant, but we need to have a time controlled function that is the sine, and I specify the amplitude. Also, you can specify the RMS value. So the amplitude here is 326. The phase is 0, and this is the frequency. So you can see this sign here now. Let me copy and paste these voltage sources, E1, E2. This is E1, E2, and E3. You can drag the tags and place close to elements. Yes, now this looks better. The phase of this voltage source is 120, and the phase here is 244. E3 that we have here. So then we can connect the ground to the phase 1, 2, and 3. So from here, you can, from the components, you can select the ground component in the search. If I search ground, we have the mechanical ground and this electrical ground. Also, you can press the G, right, to generate the ground. So I hold the control key and press the G. Yes. Now I can place this ground element here, rotate, and yes. So copy, paste, and paste it here. Yes, you can use the shortcuts to generate the grounds faster. So we have these connections till now, and now I am going to create the three-phase rectifier. So we should place the diode components. Here we have the semiconductors system level, and we can select this diode D1. Let's have a look on its properties. We have different types for the mathematical model of this diode: the equivalent line, exponential function, and XY data points. So let's use this default model. This is the forward voltage, bulk resistance, and the reverse resistance that is very high. I think also here you can see the properties of the diodes. Here the model is exponential function, and we can see the properties here, like saturation voltage and so on. So exponential voltage, the saturation current is 1 picoamps. Yes, 1 picoamps. The thermal voltage is 35 millivolt. 35 millivolt. The value of reverse resistance 100 kilo. Oh, yes, this value. So, yes, I consider the same model that is presented here in the document. So I can copy and paste, select, copy and paste this element here and here. Again, copy these three elements and paste them here. Then we can make the connections. Yes, for this three-phase rectifier. So then we should have these connections. This phase is connected to the first line, the second line, and the third line. Yes. So the first line, second, and the third one. You know, when we have the correct connection, you should see this dot. Yes, field circle. So we can make sure that the connection is correct. Then we should place a filter capacitor. From here, we can select the capacitor, and yes, we have this connection to the positive DC bus line, and this is the negative of, yes, the output voltage. And here is the load resistance and the load inductance 1.2. Oh, is the value of, yes, the value of load resistance. So again, we need to place a resistor. You can modify connections, when I move the resistor, I can modify the wires after that again. So this is 1.2 ohm, and we have this inductor here. Its value is 9.5 millihenry. So yes, it's equal to 9.5, and the unit here is the millihenry. Yes. So let's save the project. We placed the components and we set values. Now we are ready to define the analysis setup and run the simulation. Here we can check the results according to elements that we have in the model. You can select each of these curves to plot the current values or voltage values. You can see the voltage of the elements, the name of element, and the voltage. For example, the name of this element is R1. Here you can specify, do you need to have its output voltage or current waveform in the results or no. We have these two checks here, and consequently you can see these values, these variables in the report generator. Yes, so you can plot the value of current or voltage for each element. The next step is to define the solution option. Here you can see the analysis. This is the default one, and here you can add the solution setup, transient, AC or DC. So we have a transient solver here, and you can set the maximum time or the end time of the simulation, the minimum time step and the maximum time step. This is an adaptive solver. Yes. So here let's check what is the minimum and maximum time steps. So this is 0.1 second is the maximum time. The minimum time step is 1 microsecond. The maximum one is 0.5 millisecond. Yes. Excuse me, this is second. Yes. So you can add the solution options. Also here we have TR, and also you can set the properties of the solver. Yes, to manage the properties of the solver that we have this for this transient analysis. So here you can set the integration formula, that is Euler, adaptive, trapezoid, Euler, trapezoid, and set the properties of the solver here. So here you can see the properties that we have here, but I don't add this option and want to run this simulation by the default properties that we have for these solvers. So let's analyze. Here you can see the progress. simulation completed. That is too fast. Yes. And now we can generate the graphs. Here you can see the voltage sources, the value of voltage of E1, E2, and E3. So rectangular plot, voltage. I select E1, hold the control key, E2 and E3, and generate the new report. Yes. What is the maximum value? Is equal to 326. Yes. We defined these voltage sources by amplitudes, not RMS values. So the peak value is 326. Okay, now let's plot the value of the smoothing capacitor voltage. So from here, rectangular plot, the voltage of the C1. Okay, so why we have this waveform? Let me check what is the value of the capacitor 1E minus 6. I didn't set the value of the capacitor correct, I think, in the model. So let's check. The value is 1 millifarad is equal to 1 millifarad. You know, here in the output display, also you can show the value of the capacitance. Yes, right? To see the value here and check if you are setting the value of the voltage correct or no. Anyway, so let's repeat the simulation. We set the value of inductor correct and the value of, yes, the value of the resistance. Here you can see this waveform. We have fluctuations around this voltage 500. Yes. But as you can see in this figure, the value of voltage starts from 0, you know. But this graph seems to be wrong. Here, for the inductor and the capacitor, we can set the initial value of the current and voltage. So the initial value of current for the inductor is 0. We can set the initial values. And the initial value for the voltage is 0 for this capacitor. And considering these settings, we can repeat the simulation. So intentionally, I run these kind of simulations to explain to you, if you don't set these items, what kind of graphs you may get. Yes. So if you don't set the initial values, graphs is like that. If the value of capacitor is wrong, the graph is like that, and so on. Also, we can plot the value of the load current, the current of, this is R4, close to 400 amps. Yes, similar to this graph and this graph that we have for the voltage and current. So we replicated this simulation. We generated these graphs for the voltage, load current, and so on. And here I am going to explain also a parametric analysis. Suppose we are going to change the value of this capacitor and run simulations again and again to find a good value for this capacitor to have a smooth voltage with a low ripple in the output. So here you can define this local parameter, or here I can define this parameter capacitor, see all the filter capacitor. If I press enter, here you can see this window. Do you want to add the variable? Yes. The default value of the variable is 1 millifarad. This is the capacitance, millifarad. And yes. So here you can see this defined variable. And now I am going to add a parametric study. And I want to change the value of filter capacitor from 1 to 10 millihenries. The step is 1. So add this parametric study. Here you can see the values. I want to change the value of the capacitor 1 by 1. Yes, to find the best value that is suitable for this load. Yes, we can plot the voltage waveforms and decide. So I select the corresponding solver, and now let's save the design and run the parametric analysis. So here you can see we have 10 variations, and now I can plot the value of the voltage of the first option that we have. You can see the value of the filter capacitor, but I need to plot the waveforms for all options that I have here. So let me check rectangular plot. Here we can select the optometric setup. So in this graph, I should select the parametric one, voltage of the capacitor, apply trace. Yes, this is really good software. Yes, you can do this kind of parametric studies, and you can check the value of the voltage here when this is the waveform when the value of the filter capacitor is 1 millihenry, 2, 3, 4, 5. Yes, as you can see, when we increase the value of the capacitance, the ripple in the voltage is lower and lower, also for this case. And you can plot also the value of the load current versus capacitor value. Yes, as long as we increase the value of filter capacitor, we have a DC current, right? The ripple of the current is lower and lower. Anyway, in this video, just I wanted to redo this getting started example provided in the document of the ANSYS Simplorer software, the twin builder. And in the next video, we will discuss the second example, that is the hysteresis current controlled DC motor startup. Yes. So thanks for watching.